Sound actually is just vibrating air. The peripheral auditory system converts these sound waves into electrical signals. At the external ear, sound is filtered by the pinna. If the sound source is elevated, higher frequencies are transmitted better than when the sound source is at ear level. Sound travels through the auditory meatus to the tympanic membrane, also called the eardrum. In the middle ear, the pressure is increased 200 times. One reason for this is that the tympanic membrane has a larger surface than the oval window. Besides, the ossicles increase pressure because they act like levers. This is the inner ear, and it mainly consists of the cochlea. If you uncoil the cochlea, it is 3.5 centimeters long. The cochlear partition almost completely bisects the cochlea. The partition divides the cochlea into the scala tympani and the scala vestibuli. The scala media runs within the cochlear partition. The cochlear partition supports the basilar and tectorial membranes. When sound arrives at the oval window, the fluid in the cochlea starts to vibrate and the basilar membrane resonates. The basilar membrane is shaped like a trapezoid. High frequencies resonate at its base, where it is narrow and stiff. At its apex, it is wider and flexible. Lower frequencies resonate here.
Resonation of the basilar membrane makes the stereocilia at the top of the hair cells move back and forth. This changes the membrane potential of the hair cells. Stereocilia movement changes the membrane potential of a hair cell. A hair cell has stereocilia, hairs, on top of its cell body. It synapses onto an auditory nerve fiber. Resting state, some potassium channels at the tips of the stereocilia are open. Through these, some potassium flows in. When the stereocilia bend away from the longest ones, the tip links, which connect the tips of stereocilia, are compressed and the potassium channels close. Potassium can't enter the cell. This hyperpolarizes the cell. When the stereocilia move in the opposite direction, the tip links are stretched out and more potassium channels open. A lot of potassium enters the cell. This depolarizes the hair cell and opens voltage-gated calcium channels. Calcium flows into the cell. Calcium causes vesicle fusion so that the neurotransmitter is released. This neurotransmitter is sensed by the auditory nerve fiber that becomes activated. Calcium is also important for repolarization at the cell body. Here it opens calcium-gated potassium channels. Potassium leaves the cell through these channels and the cell repolarizes. Potassium is responsible for quick depolarization and repolarization of the hair cell. It flows from the scala media through the hair cell to the scala tympani. The scala media is potassium rich, while the scala tympani is poor in potassium. So the potassium flow is mainly driven by a concentration gradient. Auditory information is encoded in two ways: temporal and spatial. Sounds with frequencies smaller than 3 kHz are temporarily encoded. The membrane potential varies in the same way as the stereocilia move back and forth. This is called phase lock. Besides, all sound is spatially encoded. For this, the architecture of the basilar membrane is important. Each auditory nerve fiber gets input from a single hair cell. So auditory nerve fibers connected to a hair cell at the base of the basilar membrane convey information about high-frequency sounds, while nerve fibers connected to a cell at the apex of the membrane encode low-frequency sounds. Spatial coding of frequencies is also called tonotopy, a topographical mapping of frequencies. The auditory nerve fibers are tuned. Each has its own characteristic frequency. This is the frequency to which a fiber is most sensitive. Fibers at the base of the basilar membrane have high characteristic frequencies. Fibers at the basilar membrane's apex have low characteristic frequencies.
So, to sum it all up, a take-home message. The ear is very sensitive. It can detect a molecular movement as small as 10 picometers. The external and middle ear collect sound and amplify the pressure. Within the inner ear, membranes resonate, which makes the hair cells signal. Auditory information is encoded in two different ways, namely temporally and spatially.